Quantum computers are not just faster machines. They are forcing scientists to look again at the deepest rules of reality itself. Inside their fragile circuits, matter behaves in ways that ordinary experience cannot easily explain, where information, probability, and observation become part of the same hidden structure. This journey moves from the vast universe to the smallest particles, revealing where neutrons exist, why they are hidden inside matter, and why a free neutron cannot last forever. If this kind of calm science documentary helps curiosity stay awake while the mind slows down, please like the video, subscribe to the channel, and let the journey begin. Across the public world, quantum computing stands as a careful scientific effort surrounded by strong language, bright images, and uneven expectations. It appears in government programs, university laboratories, company roadmaps, investment reports, and headlines that often speak faster than the machines themselves can work. The technology is real, but it does not sit in ordinary life in the same way as a phone, a laptop, or a data center. It remains mostly behind controlled doors, inside research buildings where teams build, test, cool, shield, measure, and correct delicate devices. At this outer threshold, the subject is not yet the hidden nature of reality itself. It is first a human project made of funding, instruments, training, caution, and slow progress. The phrase quantum computer often carries a sense of sudden arrival, yet the public version of the field grows from many decades of physics and computer science. Researchers learn that the rules governing atoms and light can, in some limited cases, be used as a form of computation. A quantum computer is not simply a faster classical computer. It is a machine designed to process quantum information, meaning information stored in physical systems that follow quantum mechanics. Quantum mechanics is the scientific framework used to describe matter and energy at small scales, such as atoms, electrons, and photons. In public language, the idea can seem strange because the behavior of these small systems does not match everyday experience. In scientific work, it is not treated as magic. It is tested through instruments, repeated measurements, and mathematical models that must agree with observation. The outer public story is shaped by contrast. On one side, there are real achievements. Small quantum processors operate in laboratories. Cloud access allows researchers and students to run limited experiments on remote machines. Companies report progress in device size, control quality, and error reduction. Governments support national programs because secure communication, advanced materials, chemistry, and computing capacity all matter to future economies. Universities train physicists, engineers, mathematicians, and computer scientists who share a common task. They try to turn fragile quantum effects into stable tools. This work is serious and measured. On the other side, the public story often becomes too large. Some claims suggest that quantum computers are about to break all codes, replace all supercomputers, or explain consciousness, time, and the universe in one step. These claims do not reflect the careful limits of the field. Current quantum computers remain noisy, limited, and difficult to scale. They can demonstrate important principles and perform selected tasks, but they do not yet provide broad, everyday advantage over classical machines. This does not make them failures. It places them in the long early stage of a demanding technology, where each improvement is useful, but no single result settles the future. The title idea of a terrifying truth about reality belongs more to public feeling than to scientific conclusion. Quantum computing does not reveal terror in a literal scientific sense. It reveals that the physical world can store and transform information in ways that are not intuitive to the human mind. Ordinary experience comes from large objects, warm environments, and constant contact with air, light, and surfaces. A table seems solid, a stone seems fixed, and a shadow seems simple. Quantum devices are built from systems where these everyday impressions are not enough. The public threshold is therefore a place where familiar ideas begin to loosen, but they do not collapse into fantasy. They become more precise. Research institutions present quantum computing as a field with promise and restraint. NASA studies quantum methods where they may help with optimization, simulation, and scientific modeling. National laboratories examine materials, sensors, and computing architectures. Standards organizations prepare for a world in which some present encryption methods may need protection from future quantum attacks. This creates a sober kind of urgency. It does not mean that ordinary digital security has already vanished. It means that governments and industries prepare early because security systems take many years to replace. The outer social layer of quantum computing is therefore practical. It is concerned with planning, infrastructure, education, and risk. The industry around the field is also careful beneath the surface. A quantum processor is only one part of a larger system. There are control electronics, software tools, fabrication methods, calibration routines, and teams that interpret results. Public images may show golden cooling equipment or polished chips, but the wider technology includes ordinary workstations, cables, pumps, clean rooms, and data analysis. Progress often appears as improved reliability rather than dramatic transformation. A smaller error rate, a longer useful signal, a cleaner measurement, or a better manufacturing step can matter greatly. These changes are not theatrical, but they are the real path by which a scientific instrument becomes an engineering platform. At the public boundary, the language of proof also matters. Scientists do not say that a machine reveals the final truth of reality because it performs a limited calculation. They describe what the device does, how it is tested, how often it succeeds, and how the result compares with known methods. Some experiments show that quantum devices can produce patterns that are extremely hard to reproduce with classical computation. Such demonstrations are important, but their meaning is narrow. They show that quantum behavior can be controlled enough to perform a selected task. They do not show that all hard problems are solved. They do not remove the need for verification. They do not end scientific uncertainty. The calm view begins by placing quantum computing among other instruments that extend human reach. Telescopes make faint galaxies visible. Particle accelerators reveal short-lived particles. Space probes measure distant worlds. Quantum computers, in their current form, are instruments that allow researchers to shape and read quantum systems. Their importance comes from the fact that nature itself uses quantum rules. When a tool uses the same kind of rules, it may study certain parts of nature more directly than a classical machine can. This possibility is one reason the field attracts attention from chemistry, physics, materials, science, and mathematics. The outer region of the subject is therefore not a doorway into fear. It is a doorway into scale and patience. The machines are expensive, sensitive, and unfinished. The science behind them is well tested, but the engineering remains difficult. The public imagination reaches for dramatic words because quantum theory unsettles common sense. The scientific community uses slower words because real knowledge depends on limits. Observations indicate that quantum systems can be controlled well enough to compute in special ways. It remains uncertain how quickly large, fault-tolerant machines will arrive, and how broad their practical impact will be. At this threshold, the world sees a technology that is both powerful and incomplete. It does not replace ordinary reality. It shows that ordinary reality is only the surface where large things behave in familiar ways. Beneath the public claims and the polished images, there is a disciplined effort to build machines that obey the deep rules already present in matter. The first region remains outside the processor, in the institutions, expectations, promises, and cautions that surround it. From here, the subject stays grounded. It begins with the human world looking toward a machine that is not yet common, not yet simple, and not yet finished. In the outer layer of ordinary computing, information appears stable, sharp, and familiar. A classical computer works with bits, and a bit is a physical state used to represent one of two values. In common language, these values are often called 0 and 1. Behind that simple description there is always matter. A charge sits in a circuit, a voltage rises or falls, a tiny region of memory holds one condition rather than another. The machine uses physical parts arranged so that two different states can be made, protected, copied, moved, and read. The reliability of modern computing comes from the ability to make these states behave almost as if they were perfectly definite. A classical computer is built from layers of design that hide the small disorder of the physical world. At the lowest level, electrical signals pass through materials shaped into transistors. A transistor is a small switch that can control the flow of electrical current. Many transistors join together to form logic gates, and logic gates combine signals according to fixed rules. These rules are simple, but they can be arranged in vast numbers. From them come arithmetic, memory, images, sound, communication, search, and simulation. The important boundary begins with definiteness. In a classical machine, a bit is meant to be in one recorded state at a time. It may be changed by a circuit, copied into another location, compared with another bit, or stored until later. Engineers know that real circuits contain heat, noise, and imperfections, but the design pushes these disturbances into a safe margin. A voltage does not need to be mathematically perfect. It only needs to fall clearly inside the range treated as one value or the other. It allows a message, a photograph, or a bank record to move through many machines without becoming a blur of uncertain states. Classical information is also easy to copy in principle. When a bit has a definite value, another physical system can be prepared to hold the same value. This copying is central to error control. Files can be backed up, signals can be repeated, memory can be checked. The ordinary digital world depends on this ability to duplicate and restore information. The classical model also separates the data from the path in a clear way. A program gives a sequence of instructions. The processor follows them by changing bits step by step. At each stage, the machine has a defined state, even when the state is too large for a person to inspect. A weather model, a digital film, or a map database may contain enormous amounts of information, but the underlying principle remains the same. The machine moves from one definite arrangement of bits to another definite arrangement. The complexity lies in the number of steps and the amount of data, not in any loss of the basic classical rule. This way of computing has extraordinary reach. Classical computers can model bridges, control aircraft, guide spacecraft, search large archives, train statistical systems, and help analyze signals from telescopes. An algorithm is a set of instructions for solving a problem or carrying out a task. The success of classical computing comes from finding useful algorithms and then building machines that perform the required steps faster, with less energy and with fewer errors. Yet there are boundaries inside this success. Some problems grow so quickly that direct calculation becomes impractical. A molecule with many interacting electrons can be difficult to describe because each electron is connected to the others through quantum rules. A complex optimization problem can have a vast number of possible arrangements, too many for direct search. A cryptographic problem may be designed so that finding a hidden key by classical trial takes longer than any useful time. These limits do not mean that classical computers are weak. They show that some structures become too large for ordinary step-by-step exploration. The boundary between classical and quantum information appears when the physical system used for information no longer behaves like a bit with only one definite recorded state before measurement, a quantum bit, or qubit. is a physical system treated according to quantum mechanics rather than only classical rules. The difference is not that a qubit is simply smaller. Classical bits can also be very small. The difference is in the allowed state of the system and in how that state changes before it is read. A classical bit is designed to resist ambiguity. A qubit is designed to preserve a controlled form of quantum possibility until a measurement produces an outcome. This distinction is often softened in public explanation, but it is central. A quantum computer does not gain power by trying every answer in the ordinary sense. That description is too loose. The machine uses quantum states whose mathematical descriptions can combine possibilities, and it applies operations that change the pattern of those possibilities. Later, a measurement gives ordinary classical information, because every displayed result is finally a definite record. The useful part is not an unlimited collection of parallel worlds available for reading. It is the controlled shaping of probabilities so that certain answers become more likely for certain kinds of problems. At the classical boundary, measurement is ordinary and mostly harmless. Reading a stored bit reveals the value that the system has been built to hold, and the value can often remain available after the reading. A file can be opened many times. A memory register can be checked and copied. The act of reading may involve physical processes, but the information is meant to survive in the same form. This is one reason classical computers feel transparent. Their records are stable enough that the act of looking at them does not usually change the meaning of what is found. Quantum information does not fit this habit. It must eventually be reported as classical information. But before that report it follows rules that cannot be reduced to hidden ordinary bits in any simple way. Decades of experiments with light, atoms, and other systems support this conclusion. The classical boundary is therefore not merely a limit of present engineering. It is a difference in the physical description of the information itself. Classical computers remain the outer familiar shore. Where states are definite, copying is routine, and error control rests on firm duplication. Quantum computing begins where these comforts no longer apply, and where the same word information starts to carry a deeper physical meaning. Inside the controlled rooms where quantum processors are kept, the machine no longer resembles the ordinary image of a computer. It is not mainly a screen, a keyboard, or a box beneath a desk. It is an environment built around protection. The processor at the center is small, but the structure surrounding it is large, layered, and careful. Cabinets hold control systems. Cables carry signals through metal fittings, pumps, cooling stages, filters, and shielding surround the device like a quiet industrial shell. The purpose of this outer hardware environment is not display or convenience. It is to hold a small physical system apart from the restless motion of the wider world. The wider world is never still. Air molecules strike surfaces. Heat moves through metal. Electrical fields drift through rooms. Vibrations pass through floors. Light leaks through gaps. Radio waves from communication systems fill the background. In ordinary electronics, these influences are managed by design margins and error correction at the classical level. In quantum hardware, they can become direct threats to the useful state of the device. The machine must therefore create a protected space where the processor can be guided without being overwhelmed. The outer environment is a boundary between daily physics and the much quieter conditions required for controlled quantum behavior. Many leading quantum computers operate at extremely low temperatures. Some use dilution refrigerators, which are cooling systems that can bring a device close to absolute zero. Absolute zero is the lowest possible temperature on the thermodynamic scale, where thermal motion reaches its minimum allowed limit. The processor does not reach that exact limit. but it may operate at temperatures only a small fraction of 1 degree above it. In such cold conditions, unwanted thermal energy is reduced. The metal structure of the refrigerator often descends in stages, each colder than the one above, with the processor placed near the coldest region. Public images often show a hanging assembly of gold-colored plates and cables. But the meaning of the structure is simple. It is a path for taking heat away, and a path for bringing carefully shaped signals in. Cooling is not needed for every kind of quantum hardware in the same way. Some platforms use trapped ions, which are charged atoms held in place by electric fields. Others use neutral atoms controlled by light, photons moving through optical systems, defects in solid crystals, or spins in semiconductor devices. Each platform has its own outer environment. Some need vacuum chambers, where air is removed so atoms or light can move with fewer collisions. Some need lasers with stable colors and directions. Some need magnetic shielding. Some need exceptionally clean fabrication and stable electrical control. The shared principle remains protection. The hardware must reduce uncontrolled contact while preserving enough contact for operation. This creates a delicate balance. A quantum processor cannot be completely sealed away from everything, because a sealed system cannot receive instructions or return results. The outer hardware must allow chosen signals to enter and leave. It must block random disturbance while admitting ordered control. This is why cables, filters, amplifiers, and timing systems are as important as the chip itself. A signal may begin at room temperature in ordinary electronics, then pass through layers that reduce heat and noise before it reaches the processor. After an operation, a faint response may travel back outward and be amplified until it becomes a classical record. The machine is a controlled exchange between isolation and access. Shielding forms another part of this environment. Quantum devices can be sensitive to stray electromagnetic fields, which are fields produced by electric charges, currents, and changing voltages. External fields may disturb the controlled signals or shift the behavior of components. Engineers use metal enclosures, grounding, filtering, and careful layout to reduce such effects. They also manage magnetic fields, because some quantum systems respond strongly to magnetism. The aim is not to remove the universe around the machine. It is to reduce the influences that matter most for the chosen device. Vibration can also matter. Floors move slightly as people walk, equipment runs, and buildings respond to traffic or weather. In many systems, these motions are small enough to ignore. In quantum hardware, they can shift optical paths, disturb alignment, or introduce noise into sensitive instruments. Laboratories often place equipment on stable tables, isolated platforms, or carefully designed supports. Lasers, mirrors, lenses, wires, and vacuum chambers must remain aligned over time. A small drift can become a large problem when the experiment depends on timing and precision. Clean fabrication belongs to the same outer region. Some quantum processors are made in facilities that control dust, chemical contamination, and surface quality. A speck of unwanted material or a small defect can alter electrical behavior. Superconducting circuits depend on thin films, junctions, and patterned structures made with high precision. Semiconductor spin devices depend on materials where electrons can be confined and controlled. Photonic devices depend on channels that guide light with low loss. These parts are not abstract. They are physical objects with edges, surfaces, impurities, and stresses. The hardware environment begins before the machine is turned on, in the way matter is shaped. Control systems translate human instructions into pulses. A pulse is a short controlled signal, such as a change in microwave, laser, or electrical energy. The timing, strength, and shape of these pulses must be stable. If they arrive too early, too late, too strong, or too weak, the processor may not perform the intended operation. Calibration becomes a constant part of the environment. The machine is measured, adjusted, measured again, and adjusted again. This does not mean the science is uncertain in a loose sense. It means the physical device must be tuned, because real materials are never perfectly identical, and real conditions drift over time. The hardware environment also shows why quantum computing is not merely a software revolution. It is a meeting of physics and engineering. The code that runs a quantum experiment depends on wires, cold stages, vacuum pumps, lasers, amplifiers, filters, and fabrication tools. The result depends on whether the environment can keep disturbances small enough for long enough. In this region, reality appears not as a dramatic mystery, but as a patient demand. Matter must be cooled, shielded, cleaned, aligned, and controlled. The outer machine room teaches that quantum information is not floating free. It is carried by physical systems that must be protected from the noise of ordinary existence. A quantum processor becomes meaningful only when its small working parts can hold a quantum state long enough to be controlled. In this region, attention moves from the surrounding machinery to the physical carriers of quantum information. These carriers are often called qubits, and each one is a real system with a measurable condition. A qubit may be formed from a tiny electric circuit, an ion held in a trap, an atom controlled by light, a photon moving through an optical path, or a small magnetic property inside a material. The name is shared, but the bodies are different. Each platform chooses a part of nature that can be prepared, guided, and read to serve as a unit of quantum information. A quantum state is the complete scientific description used to predict the possible outcomes of measurements on a quantum system. It is not a visible cloud around the object, and it is not a hidden picture waiting inside the machine. It is a mathematical and physical description linked to preparation and measurement. A laboratory does not see the state directly in the way a person sees a stone on a table. It prepares the system in a controlled way, applies a known operation, measures the result, and repeats the process. From these records, the behavior of the state is understood. The fragile state is therefore physical and statistical. It belongs to a real object, but its full meaning appears through trials. The fragility begins because a qubit must remain separated from uncontrolled influence, while still being available for control. If a qubit interacts too strongly with its environment, the useful quantum description changes in a way that removes the delicate features needed for computation. This loss is called decoherence, meaning the fading of ordered quantum relationships into ordinary-looking classical uncertainty through contact with surrounding degrees of freedom. The word sounds technical, but the idea is plain. A quantum state can carry a kind of order that is easily disturbed. Heat, stray fields, unwanted light, material defects, and imperfect signals can all provide paths for that order to leak away. In a superconducting circuit, the qubit may depend on collective electrical behavior in a carefully patterned material. The circuit is large compared with a single atom, but it is engineered so that only selected low-energy states matter. It must be cooled deeply so thermal energy does not shake it into unwanted behavior. Its metal films and junctions must be made with care, because microscopic defects can absorb energy or shift the system. Its control pulses must be shaped with precision because the state does not tolerate rough handling. The circuit is built to act like a quantum object, but it remains a piece of matter. In an ion trap, the qubit may be stored in internal states of charged atoms. The atoms are held away from surfaces by electric fields inside a vacuum chamber. Laser light can cool them, prepare them, and change their states. Their isolation can be strong, because an atom is naturally identical to another atom of the same element. Yet the trap is still not perfect. Electric field noise, laser instability, unwanted motion, and collisions with remaining gas can disturb the system. The qubit is fragile because useful information depends on exact control of a state that must stay clean while being acted upon. Neutral atom systems share a related balance. Atoms without net electric charge can be held in patterns made by light. Their positions can form arrays, and their internal states can be controlled by laser pulses. The atoms are simple in one sense, but the surrounding apparatus is not simple. The light must be stable. The vacuum must be good. The atoms must be placed and held long enough to perform operations. Any loss of an atom changes the working register. Photonic qubits use particles of light. Light can travel with little disturbance in some settings, which makes photons useful for communication and certain forms of computation. Yet photons can be lost in fibers, waveguides, lenses, or detectors. A missing photon is not a small inconvenience when it carries a qubit. It is a missing part of the information. The fragility may not be a slow fading of a stored state, but the simple fact that light must be generated, routed, interfered, and detected with low loss. Other qubits may use spins. Spin is a quantum property linked to magnetic behavior, though it is not a literal spinning ball. Electron spins or nuclear spins can hold quantum information in selected materials. Their challenge comes from the surrounding material, where nearby nuclei, charges, defects, and fields can disturb the spin state. The qubit is embedded in a solid, and the solid is both support and source of noise. Across all platforms, the fragile state is not an abstract weakness. It is the price of using quantum behavior as information. A classical bit survives because it is built to fall into a stable, easily recognized condition. A qubit must avoid settling too soon into the kind of definite record that ordinary machines prefer. It must be stable enough to persist, but not so locked in place that it cannot be guided. It must be isolated enough to keep its state, but connected enough to receive operations and produce a result. This balance makes every qubit a narrow physical agreement between nature and engineering. Time becomes an important measure of this agreement. Researchers speak of coherence time, the period over which a quantum state keeps useful order before disturbance becomes too large. Longer coherence time helps, but it is not enough by itself. The operations must also be fast and accurate compared with that time. A qubit that keeps its state for a long period but cannot be controlled well is not a useful computing element. A qubit controlled quickly but disturbed too often is also limited. The real question is how many reliable operations can occur before the state loses the order needed for the task. The fragile quantum state shows the next inward step of the machine. Here the protected thing becomes clear. It is not a miniature version of ordinary memory. It is a prepared physical state that must remain delicately ordered under strict conditions. Observations indicate that many kinds of qubits can be prepared and controlled well enough for real experiments. It remains uncertain which designs will scale most effectively into large, reliable machines. In this region, each qubit is a small, quiet test of whether matter can be persuaded to hold information in a form that everyday experience does not naturally preserve. Superposition is the first inner rule that makes a qubit different from an ordinary bit. It is often described publicly as being both of two things at once, but that phrase is only a rough doorway. A clearer scientific description is that a quantum system can be prepared in a state that combines the possible outcomes of a chosen test, with each outcome carrying a probability weight and a phase. Phase is a part of the quantum state that affects how possibilities later reinforce or cancel each other. It is not a hidden label that can be read like a note. It is part of the structure that gives quantum behavior its special form. In an ordinary classical setting, a small object may be unknown because a person has not looked at it. A coin under a cup may already have one face up, even if no record has been made. The uncertainty is in the observer's knowledge, not necessarily in the object. Superposition is different. In tested quantum systems, the state cannot always be treated as a secret classical value waiting to be uncovered. Experiments show patterns that match the quantum description and do not fit a simple picture in which every result is already fixed in the ordinary way. This is why superposition is not just ignorance. It is a physical feature of the prepared state. A qubit has a simple image, although the real mathematics is exact rather than visual. The ordinary bit has two basis states, which can be named 0 and 1. A basis state is a reference state used to describe other states. A qubit can be prepared in either basis state, but it can also be prepared in a controlled combination of them. The combination is not like a mixture in a bowl, where small pieces of each ingredient sit side by side. It is a single state whose future behavior depends on the relation between its parts. The important feature is not merely that there are probabilities. The important feature is that the parts of the state can interfere. Interference is a familiar word from waves. Water waves can meet and rise higher together, or meet crest against trough and become flatter. Light can also show interference when paths are arranged with enough control. Quantum interference is not exactly the same as a visible ripple on water, but the guiding idea helps. The probability structure of a quantum state can be shaped so that some outcomes become stronger and others weaker. In a qubit, phase controls the way this shaping happens. A tiny change in phase can change the pattern produced by later operations. This makes superposition powerful, but it also makes it sensitive. Superposition does not mean that a quantum computer gives every answer freely. That common image hides the discipline of the process. A useful quantum calculation must arrange operations so that unwanted possibilities tend to cancel, and wanted possibilities tend to remain. If the superposition is made carelessly, the final record may show only a random-looking result. The state must be prepared, rotated, combined, and protected according to a clear design. A quantum operation is a controlled change applied to the state. It is a physical transformation that follows the rules of quantum mechanics. In a superconducting qubit, superposition may exist as a combination of two selected circuit states. The circuit is macroscopic compared with an atom, but it is engineered so that quantum rules apply to the chosen electrical behavior. Microwave pulses can place the circuit into a superposition. The pulse has a shaped duration, strength, and frequency. It does not push a switch from one side to another in the ordinary sense. It changes the state in a continuous way within the allowed quantum description. The state can be guided through many possible orientations before it becomes part of a recorded outcome. In an ion or atom, superposition may involve internal energy states. An atom can be prepared so that its quantum description includes more than one selected state with a definite relation between them. Laser pulses can create and control this relation. The atom remains one atom. It is not physically split into separate ordinary objects. Its state is described by a combination that becomes evident through repeated experiments. Each single trial gives a definite record. But many trials reveal the pattern predicted by the superposed state. The care needed for superposition shows why the surrounding environment matters so much. Thermal motion, stray fields, unstable pulses, or material defects can disturb phase. When phase information is lost, the state begins to behave more like an ordinary mixture. A mixture is a situation where a system is in one condition or another with certain probabilities, but without the special quantum relation that allows interference to keep superposition useful. The device must preserve both the probability weights and the phases. Losing either one changes the computation. Superposition also changes the meaning of control. In ordinary computing, a control step may flip a bit or leave it unchanged. The bit begins in one definite value and ends in another definite value. In quantum computing, A control step can move a state through a continuous space of possibilities. It can turn a basis state into a balanced superposition. It can change phase. It can reverse a previous operation if the system has remained sufficiently isolated and the operation has been applied accurately. This reversibility is part of the mathematical structure of ideal quantum evolution. Real devices approximate it, limited by noise and imperfect control. The truth revealed by superposition is quiet but deep. At small scales, physical possibility is not always a list of ordinary facts waiting to be exposed. It can be a structured state that carries relations among possible outcomes. The relations are measurable through repeated preparation and comparison with predictions. They are not visible in a single glance. They do not invite exaggerated conclusions about thought, fate, or unreality. They show that nature keeps order in a form unlike everyday certainty. In this inner region, the qubit is no longer viewed mainly as hardware. It becomes a prepared relation among possible outcomes, held carefully in matter and guided by pulses, fields, or light. Superposition is fragile because it depends on phase. It is useful because phase allows interference. It is strange only when judged by the habits of large objects. Within quantum theory, it is a normal and tested feature of the world. The machine's power begins here, not in unlimited speed, but in the ability to shape physical possibility before it settles into a record. Entanglement forms a deeper layer of quantum behavior because it belongs not to one qubit alone, but to the shared state of more than one system. A single qubit can hold a superposition, with phase and probability arranged inside one physical carrier. Entanglement appears when the correct description of two or more quantum systems cannot be separated into independent descriptions of each part. The systems may be far enough apart to be treated as distinct objects, and each may still be measured in its own place. Yet their joint state carries a connection that is stronger than ordinary shared ignorance. The whole has a structure that cannot be reduced to separate private states for the parts. A simple way to describe entanglement begins with preparation. Two qubits are brought through an operation that links their quantum states. After that operation, the pair has one shared state. Measurement of one qubit gives a definite result, and measurement of the other also gives a definite result. Across many repeated trials, the results show correlations, meaning patterns of connection between the outcomes. Classical objects can also be correlated. Two sealed boxes may contain matching cards because they were packed together earlier. Opening one box reveals something about the other, but the hidden contents were fixed in the ordinary way. Entangled systems show correlations that experiments indicate cannot be explained by this simple hidden card picture. The strongest evidence comes from tests based on Bell's theorem. Bell's theorem is a result showing that certain predictions of quantum mechanics cannot be reproduced by a broad class of local hidden variable theories. Local means that an event is not influenced faster than light by a distant event. Hidden variables are imagined unseen properties that would determine outcomes in advance. Experiments with photons, ions, atoms, and other systems support the quantum predictions. They show that nature does not fit a simple model, in which every measurement result is already fixed locally in an ordinary way. This is one reason entanglement changes the philosophical landscape around reality, even while it remains a precise laboratory phenomenon. Entanglement does not allow useful messages to travel faster than light. This point is central. When one part of an entangled pair is measured, the result at that location is not controlled in a way that can carry a chosen message to the other location. The correlations become clear only when records from both sides are later compared through ordinary communication. The shared state is non-classical, but it does not break the communication limit set by relativity. The unease comes from the fact that the world seems to contain relationships that are not built from independently settled parts. The calm scientific view holds both facts together. Entanglement is real, and faster-than-light signaling does not follow from it. In quantum computing, entanglement is not only a philosophical marker, it is also a working resource. Many quantum algorithms depend on operations that entangle qubits, so that information is stored across a joint state rather than in separate carriers. The machine then applies further operations that change the shared structure. The useful behavior does not come from each qubit carrying its own private answer. It comes from the way the group state evolves. A register of qubits can hold patterns of relation that no list of independent classical bits can describe efficiently in general. This is one source of the difficulty classical computers face when simulating large quantum systems. The number of possible basis states for a register grows rapidly as qubits are added. With each additional qubit, the mathematical description of a general quantum state becomes larger. This growth is sometimes described as the source of quantum power, but the statement needs care. A large quantum state is not automatically useful, and it cannot be read out completely in one measurement. A measurement produces a limited classical record. The power of entanglement appears only when operations shape the joint state, so that measurement has a useful chance of revealing the desired structure. Entanglement gives access to richer relationships, but it also demands precise control. Entanglement is fragile for the same broad reason superposition is fragile, but the fragility now spreads across a relation. If one qubit in an entangled group interacts with the environment in an uncontrolled way, the shared state can degrade. The environment may carry away information about the system, and the clean relation among qubits becomes less useful. This is why entanglement is difficult to maintain as devices grow. Each qubit adds possible pathways for disturbance. Each operation introduces possible error. The inner relation must be created, preserved, and used before noise erases the pattern. Different hardware platforms produce entanglement in different ways. Superconducting circuits may couple through microwave resonators or direct circuit interactions. Trapped ions may share motion in a collective mode, allowing laser pulses to link their internal states. Neutral atoms may interact when placed in highly excited states, making one atom's condition affect another's allowed behavior. Photonic systems may create entangled light through optical processes and then guide it through interferometers or fibers. In every platform, the physical method differs, but the goal is the same. Separate systems are brought under a shared quantum description that can later be tested and used. Entanglement also changes the meaning of locality and the inner language of the machine. Ordinary objects appear to carry their properties with them. A stone keeps its mass and shape whether another stone is touched across the room. Entangled qubits do not behave as if all measurable properties simply belong to each part in advance. The state belongs to the pair or group. This does not make the systems mystical, it makes them non-classical. The word non-classical means that the behavior cannot be fully captured by the concepts that describe everyday objects. Quantum computing turns this relation into something practical enough to engineer, though still difficult enough to limit every present machine. At this layer, the truth about reality becomes less like a dramatic secret and more like a quiet correction. The world is not always assembled from small parts that each carry complete independent facts before being observed. Sometimes the best tested description belongs to the relation among parts. Entanglement shows that physical reality can be deeply relational without becoming vague. It has rules, limits, and measurable patterns. It resists ordinary intuition, yet it remains exact enough to guide machines, predict experiments, and define the shared states at the heart of quantum computation. Measurement is the layer where a quantum computation becomes a record. Before measurement, a qubit or a group of qubits is described by a quantum state. That state may contain superposition, phase, and entanglement. It may carry patterns that have no direct classical image. Yet the final output that a person, a computer file, or a laboratory instrument receives is ordinary information. A detector clicks, a voltage crosses a threshold, a counter stores a value, or software writes a result into memory. The record is definite. It can be copied, printed, compared, and stored. Measurement is the bridge between the inner quantum description and the outer classical world of evidence. A measurement is not simply looking in the casual sense. It is a physical interaction arranged to connect a quantum system with a measuring device. The measuring device is large enough, stable enough, and noisy enough in the ordinary way to leave a lasting record. In a laboratory, this may involve a pulse that maps the state of a qubit onto another physical signal, followed by amplification and detection. In a photon experiment, it may involve a detector absorbing light and producing an electrical signal. In an ion trap, it may involve laser light that makes one state shine while another remains dark. In a superconducting circuit, it may involve reading how the circuit changes a microwave signal. The details vary, but the role remains the same. The quantum state is brought into contact with a process that yields a classical outcome. The difficulty begins because a single quantum measurement usually does not reveal the full quantum state. It gives one outcome from the set allowed by the measurement. If a qubit is measured in a chosen basis, the result is one of the basis outcomes. The probabilities of these outcomes are determined by the state before measurement. After the result is recorded, the previous state is no longer available in the same form. This makes quantum measurement unlike checking an ordinary stored bit. A classical bit can often be read while leaving the same value ready to be read again. A qubit measurement generally changes the system in a way that depends on the outcome and on the measurement basis. The word basis means the set of reference outcomes that a measurement distinguishes. For a qubit, one basis may separate the states called 0 and 1. Another basis may separate different combinations of those same reference states. The choice of basis matters. A state that is definite in one basis can give uncertain outcomes in another. This is not a defect in the instrument. It is part of the quantum rule. The measurement does not uncover every possible property at once. It asks one controlled kind of physical question and receives one kind of record. The state prepares the probabilities, and the measurement defines which outcomes can appear. In quantum computing, measurement is often placed at the end of a sequence. Operations first shape the quantum state, and then measurement extracts a classical sample from it. A sample is one recorded outcome from a probability distribution. Because one sample is limited, many runs may be needed. The machine prepares the same starting condition, applies the same operations, measures, records the result, and repeats. The pattern across many results is compared with the expected distribution. This repeated process is central because quantum information cannot usually be opened like a complete file. It must be inferred through the outcomes that the measurement allows. Measurement also gives quantum computing its restraint. The inner state of a register may require a large mathematical description, but the act of measurement produces only a finite classical string. A string is a sequence of recorded values. This prevents the machine from simply handing over the whole hidden structure of its state. The computation must be designed so that useful information is concentrated into the results that can be measured. The silent work of the earlier operations matters only if the final measurement has been made likely to reveal the needed pattern. Without that design, the output may look like noise. The measurement problem is a name given to a deep conceptual issue in quantum theory. It concerns how the smooth evolution of a quantum state relates to the definite outcomes seen in measurements. The mathematical rules used by physicists work extremely well for predicting probabilities, but the meaning of the change from state to record remains interpreted in different ways. Some views treat the change as a real physical collapse of possibilities into one outcome. Other views describe measurement through the spreading of entanglement into the environment, leaving separate branches or effectively classical records. Still others take the quantum state as a tool for organizing knowledge about possible observations. The scientific predictions are the shared center. The interpretation remains unsettled. For a quantum computer, this unsettled meaning does not prevent practical work. Engineers and physicists use the measurement rules to design circuits, calibrate devices, and estimate performance. They do not need a final philosophical agreement in order to read a qubit. The detector gives records. The records have frequencies. The frequencies are checked against theory and against calibration. The machine either behaves within expected limits or it does not. In this sense, measurement is both mysterious in its deepest meaning and ordinary in its laboratory discipline. It turns fragile quantum behavior into data that can be handled. The record produced by measurement is classical because it must be stable enough to survive outside the quantum system. A laboratory notebook, a screen, or a stored file cannot remain in a delicate superposition for practical purposes. It belongs to the large, warm, interacting world where countless environmental contacts make definite records durable. This is why measurement feels final. Once the outcome becomes part of the wider world, it can be shared and compared. The private quantum state that led to it cannot be reconstructed from that single record alone. At this layer, reality shows a quiet boundary between what can exist as a controlled quantum state and what can be known as a stable result. Measurement does not make quantum computing unreal, and it does not make the observer magical. It shows that knowledge in physics depends on physical acts of recording. The quantum state guides probabilities with great precision. The measuring apparatus produces definite marks. Between them lies the narrow point where possibility becomes evidence, where the inner state gives way to the outer fact, and where a quantum computer finally says something that the classical world can keep. Error and noise form the region where the ideal picture of a quantum computer meets the physical world again. A prepared state may be shaped with care, and a measurement may produce a definite record, but between those points the device is never perfectly quiet. Every qubit is made of matter or light, and every carrier of quantum information sits near other systems. Some influences are intended, such as a control pulse or a chosen coupling between qubits. Others arrive through heat, defects, drifting fields, imperfect timing, unstable lasers, residual gas, stray photons, or flaws in fabrication. Noise is the broad name for these disturbances, and error is the change they cause. In an ideal calculation, each quantum operation follows a precise rule. The state moves in a controlled way, phase is preserved, and entanglement is created or adjusted according to design. In a real device, the operation may be slightly too strong, slightly too weak, or slightly misplaced in time. A pulse may rotate a qubit by almost the intended amount, but not exactly. A laser may have a small frequency drift. A signal may carry fluctuations. A neighboring qubit may influence the target when it is meant to remain quiet. These imperfections do not announce themselves as dramatic failures. They enter as small deviations, repeated many times. There are different kinds of error. A bit flip error changes the measured value in the chosen basis, turning one recorded outcome into the other. A phase error changes the phase relation in a quantum state. even if a later simple measurement might not immediately show a flipped value. Phase errors are especially important because phase carries the interference structure used in quantum computation. A qubit can therefore be damaged without looking damaged in one narrow test. Full control requires checking different aspects of the state, because quantum information is not held only in the final value that appears on a screen. Energy loss is another common path for error. A qubit may relax from a higher energy state to a lower one, giving energy to its surroundings. This process is often called relaxation. A separate process, just called dephasing, may scramble phase without changing energy in the same direct way. Relaxation and dephasing are not identical, but both reduce the useful order of a quantum state. They mark ways in which the environment gains influence over the system. The state becomes less able to carry the relations required for computation. Noise can be coherent or incoherent. Coherent noise has regular structure, such as a control error that repeats in a similar way each time. Incoherent noise behaves more like random disturbance. Coherent errors can build up in a systematic direction, while incoherent errors spread results more diffusely. Both matter. A machine may appear stable under one test and still fail under a longer sequence where small errors accumulate. This is why quantum devices are tested through benchmarking, calibration, and comparison. A single successful operation does not prove a processor is reliable for a long task. Decoherence remains the central word for the loss of quantum order into the environment. It does not require a human observer. It occurs when the system becomes entangled with uncontrolled surroundings in a way that makes the useful relations inside the computer fade from the accessible description. Air molecules, substrate defects, stray fields, and thermal motion can all serve as parts of that surrounding world. Once information about the qubit leaks outward, the clean state inside the computation becomes harder to use. The result is not always a sudden collapse. It can be a gradual loss of contrast, like a pattern becoming faint because uncontrolled paths carry away pieces of its order. Quantum error correction is the main scientific response to this fragility. It does not copy an unknown qubit directly, because the no-cloning theorem shows that an arbitrary unknown quantum state cannot be copied perfectly. Instead, error correction spreads one logical qubit across several physical qubits. A logical qubit is the protected unit of information encoded in a larger pattern. The system is measured in carefully chosen ways that reveal signs of errors without directly reading and destroying the encoded information. These signs are called syndromes. They indicate what correction is likely needed, while preserving the protected state as possible. This method is subtle because quantum information cannot be checked like ordinary memory. A classical file can be duplicated and compared. A quantum state must be protected by using entanglement, repeated syndrome measurements, and correction rules. The aim is to make the logical information more stable than any single physical qubit. If the error rate of physical operations is below a certain threshold, and if the errors have the right character, larger codes can in principle suppress failures strongly. This threshold idea is one reason large fault-tolerant quantum computing is considered possible in theory. Fault-tolerant means that a computation can continue correctly, even when some components make errors. As long as the error rate remains low enough and correction is applied properly, present machines do not yet have the fault tolerance needed for long quantum computation. They operate in a noisy intermediate stage, where devices are powerful enough to explore real quantum behavior, but not reliable enough to run deep calculations. This stage is useful because it reveals how hardware behaves, how errors appear, and how control methods improve. It also makes claims of performance difficult to interpret. A result may show a useful demonstration, a special advantage. or a narrow benchmark, but noise must always be examined before broad meaning is assigned. Error and noise give quantum computing its slow pace. The machines do not only need more qubits, they need better qubits, cleaner operations, stronger correction, steadier control, and architectures that can manage many measurements without overwhelming the system. Adding more physical parts can add more disturbance unless the design also improves. Scale is not simply a count, it is a question of whether the whole device becomes more reliable as it grows. In this region, the inner truth is practical and calm. Quantum reality is not fragile because it is unreal. It is fragile because its useful order depends on relations that ordinary environments easily disturb. The same world that allows a record to become stable also threatens the state before the record is made. Noise is not an outside inconvenience added after the science. It is part of the physical situation that any real quantum computer must face. The path inward pauses here because every deeper use of the machine depends on whether this quiet disorder can be understood, reduced, and corrected. A quantum algorithm lives inside the narrow space between fragile physical states and useful classical records. It is not a spell that makes a machine instantly know an answer. It is a designed sequence of operations that prepares a quantum state, changes it in controlled steps, and then measures it so that the final record has a better chance of containing useful information. The difference from ordinary computation is not only speed, it is the way the algorithm uses superposition, phase, entanglement, and interference to shape probability before measurement. The machine does not reveal every hidden value. It arranges the state so that some outcomes become more likely and others become less likely. The outer shape of a quantum algorithm can resemble a classical procedure. There is an input, a set of operations, and an output. There are gates, registers, and measurements. A gate is a controlled operation applied to one or more qubits. In ordinary diagrams, gates may look like simple blocks, but each block represents a physical transformation that must be carried out by pulses, fields, or light. The algorithm is therefore both mathematical and physical. It describes what should happen to the quantum state, while the hardware tries to make that description real. The central tool is interference. In a classical probabilistic calculation, a machine may choose random paths and count how often they lead to success. The probabilities add like ordinary chances. In a quantum algorithm, probability amplitudes guide the outcomes. A probability amplitude is a quantity whose size and phase help determine the chance of a result. Amplitudes can add or cancel. This means that a quantum algorithm can be built so that wrong paths tend to cancel and useful paths tend to reinforce. The final measurement still gives one record, but the distribution of possible records has been shaped by the earlier motion of the state. This shaping requires structure in the problem. Quantum computers do not accelerate every task. They are best suited to problems where the desired information can be encoded into a pattern that quantum operations can expose. If a problem has no useful structure, making a large superposition does not guarantee a useful answer. The machine may produce a record that is no better than a random sample. The algorithm must guide the amplitudes toward a pattern that can survive measurement. This is why known quantum algorithms are not general miracles. They are careful methods for selected mathematical and physical structures. One famous example is factoring large whole numbers into their prime factors. A prime factor is a whole number greater than one that divides another whole number evenly, and cannot itself be divided evenly by smaller whole numbers, except 1. The known quantum approach uses the connection between factoring and finding a repeating pattern. The algorithm does not simply test every possible factor. It transforms the problem into one where periodic structure can be detected through quantum operations. A periodic structure is a pattern that repeats at regular intervals. Quantum interference helps make information about that repetition more visible in the final measurement. This is why the algorithm matters for some forms of encryption, though practical impact depends on building far larger and more reliable machines than current noisy devices. Another important method is quantum search. In an unstructured search, a classical machine may need to check many possibilities. A quantum search algorithm can increase the amplitude of marked answers through repeated operations. The improvement is real but limited. It does not turn a vast search into a single effortless step. It reduces the number of steps by a particular amount under ideal conditions. The method shows how quantum interference can amplify a desired outcome, but it also shows restraint. The mathematics gives an advantage, not unlimited power. A deeper family of algorithms uses phase estimation. Phase estimation is a method for learning phase information connected to a quantum operation. Since phase is not directly visible in a single simple measurement, the algorithm converts phase relationships into measurable patterns. It does this by preparing registers, applying controlled operations, and using interference so that the final records reveal information about the hidden phase. This method is important because many quantum systems are naturally described through transformations with phases and frequencies. The algorithm works by respecting the language of quantum mechanics rather than forcing the system into a purely classical shape too soon. Quantum algorithms often begin by spreading information across a register. This spreading does not mean that every answer can later be read. It means that the state is placed into a form where many computational paths contribute amplitudes. Operations then change these amplitudes according to the problem structure. Entanglement may link qubits so that the state of the register cannot be separated into independent parts. Interference then rearranges the chances of different outcomes. Measurement finally reduces the state to a classical record. The art of the algorithm lies in making that record informative despite the narrowness of measurement. This process is easy to overstate. A quantum computer does not evade mathematical difficulty in all forms. Some problems remain hard even for quantum machines as far as current theory shows. Some speed-ups are proven only for ideal models. Some proposed advantages depend on assumptions about both quantum and classical methods. Classical algorithms also improve, sometimes changing the comparison. Therefore, each claimed quantum advantage must be tied to a precise task, a clear model, and a careful measurement of resources. A calm account does not weaken the field. It protects its meaning. Resource counting is part of this inner region. An algorithm may require a certain number of logical qubits, a certain depth of operations, and a certain accuracy. Depth means how many layers of operations must be performed in sequence. A shallow task may fit within noisy hardware. A deep task may require fault tolerance because errors accumulate. This means the beauty of a quantum algorithm on paper does not automatically become a useful application in a laboratory. The path from mathematical design to physical result passes through noise, calibration, and correction. Quantum algorithms reveal a precise kind of strangeness. They show that computation can be built from the same rules that govern small physical systems. They do not make reality into a dream, and they do not make knowledge unlimited. They show that information can be processed through amplitudes rather than only through definite values. In this layer, the machine's inner logic becomes visible. It prepares possibility, shapes, relation, lets phases meet, and accepts only the record that measurement can provide. The result is a method of calculation that is quieter than public myth, but more unusual than ordinary intuition expects. Matter is the natural home of quantum computing because matter itself follows quantum rules. As molecule, a crystal, a metal surface, or a magnetic material is not built from small classical parts that simply sit in fixed positions with fixed properties. It is built from nuclei and electrons whose behavior is described by quantum states. Electrons spread through orbitals, which are allowed patterns for where an electron may be found around atoms or across a material. These patterns can overlap, combine and change when atoms move or when light, heat, pressure, or electric fields act on the system. The result is a world where the useful description often becomes too large for ordinary calculation. Classical computers can simulate matter with great success in many settings. They help predict protein shapes, chemical reactions, battery materials, alloys, catalysts, and the behavior of solids. Scientists use approximations, meaning controlled simplifications that keep the most important features while leaving out details that are less important for the question being studied. These methods support modern chemistry, materials science, medicine, and engineering. Yet some systems remain difficult because their quantum relationships are too tangled. When many electrons interact strongly, the number of possible arrangements can grow beyond practical classical tracking. The difficulty does not come from a lack of effort. It comes from the size and structure of the quantum description itself. A quantum computer offers a different approach because it can use one controllable quantum system to represent another. This is called quantum simulation. A simulation is a model that reproduces selected behavior of a system so it can be studied. In this case, the model is not only a set of ordinary bits describing equations. It may be a group of qubits arranged so their states and operations mirror the important quantum features of the molecule or material being examined. Since nature stores the problem in quantum form, a machine that also stores information in quantum form may represent some parts of the problem naturally. The promise is clear in chemistry. A chemical bond depends on electrons shared or arranged among atoms. The strength of a bond, the shape of a molecule, and the path of a reaction all depend on the allowed quantum states of electrons and nuclei. For small molecules, classical methods can be very accurate. For larger or strongly correlated systems, the calculation becomes harder. Strong correlation means that the motion or state of one electron is closely tied to the motion or state of others, so they cannot be treated as nearly independent. This appears in many important chemical and material systems. It is one reason researchers study quantum computing for catalysts, high-performance materials, and energy-related chemistry. A catalyst is a substance that helps a chemical reaction proceed without being consumed in the final result. Many catalysts work through subtle changes in electron structure at a surface or inside a molecule. These changes can be difficult to calculate when several atoms and electrons interact in a strongly connected way. A quantum computer may eventually help estimate energies and reaction pathways more efficiently for selected cases. This would not replace laboratory chemistry. It would give researchers another tool for narrowing possibilities and understanding why certain reactions happen more easily than others. Material science offers a related region. A material's visible properties come from invisible quantum behavior. Whether a substance conducts electricity, resists heat, becomes magnetic, absorbs light, or forms a strong crystal depends on how electrons move and interact through its structure. Some materials can be described well with existing methods. Others resist simple treatment. High-temperature superconductors, certain magnetic materials, and complex quantum phases remain challenging. A superconductor is a material that can carry electrical current without ordinary electrical resistance under suitable conditions. In some materials, the mechanism behind this behavior is well understood. In others, especially those with strong interactions, important details remain unsettled. Quantum simulation may help study these many-particle systems. A many-particle system is a system containing many interacting quantum parts. The difficulty is not only the count of particles, but the web of relationships among them. If each part behaved almost independently, a classical approximation might work well. When the parts form a shared state with deep correlations, the classical description may demand enormous resources. A quantum simulator can be designed so that its own qubits or atoms form similar patterns. The scientist then measures the simulator to learn about the behavior of the modeled system. There are two broad styles of quantum simulation. In analog simulation, the device is built so its natural behavior resembles the system being studied. Cold atoms arranged by light can imitate particles moving in a lattice. Trapped ions can represent interacting spins. Superconducting circuits can model selected quantum dynamics. Analog simulation can be powerful because the hardware directly follows a chosen physical pattern, but it may be harder to correct errors or verify every detail. In digital simulation, a sequence of quantum gates approximates the evolution of the target system. Digital methods can be more flexible, but they can require many accurate operations. Verification is a serious part of this region. A quantum simulator is useful only when its results can be trusted. For small systems, classical computers can check the answer. For larger systems, direct checking may become difficult, which is exactly why the quantum device is useful. Researchers therefore use comparisons across different methods, tests on simpler cases, conserved quantities, and repeated measurements. A conserved quantity is a property that remains unchanged during a process when the rules of the model require it to stay fixed. Trust grows through agreement among checks, not through a single dramatic result. Current quantum simulations are still limited by noise, size, and control quality. They can explore meaningful models and demonstrate principles, but broad practical advantage for chemistry and materials remains an active goal rather than a completed transformation. Observations indicate that controlled quantum devices can reproduce selected behaviors of molecules and many-particle systems. It remains uncertain which applications will become useful first at large scale. In this inner region, the machine turns back toward the substance from which it is made. Metal, light, atoms, and circuits become tools for studying other metals, lights, atoms, and bonds. The boundary between computer and experiment softens, because the processor is not only calculating about quantum matter, it is quantum matter arranged to carry a question. The result is not a final revelation that reality is unknowable. It is a careful method for asking nature to model part of nature. Using the same deep rules that make matter rich, stable, reactive, and difficult to fully predict. Prediction is one of the quiet reasons computing matters. A machine is asked to take known conditions, apply trusted rules, and produce a useful statement about what may happen or what value may be found. In everyday life, prediction can seem like a simple extension of calculation. If the starting point is known well enough, and the rules are applied carefully enough, the future appears to become a matter of patience. Classical science strengthens this feeling in many places. The motion of a spacecraft can be planned with high accuracy. An eclipse can be timed long before it happens. A bridge can be tested in models before it is built. These successes are real, but they do not mean that all of nature opens itself to perfect calculation. Quantum computing enters this region by showing both new reach and new restraint. It may help predict certain properties of molecules and materials because it uses quantum states to represent quantum systems. Yet it also reminds science that prediction is not the same as possession of the full world. A quantum computer can prepare a state and guide it through operations, but the final measurement gives a limited record. Repeated measurements build a distribution of outcomes, not a complete unveiling of every internal relation. The first limit is physical information. No real experiment begins with infinite precision. A starting state is prepared with intolerances. A temperature is controlled within a range. A pulse has a measured shape, but not a perfect one. A material sample contains impurities, defects, and boundaries that may not all be known. Even when the governing equations are trusted, the input may be incomplete. Prediction depends on how strongly the unknown details affect the result. Some systems are forgiving. Small errors in the starting description remain small enough that the forecast stays useful. Other systems amplify small differences until long-term prediction becomes unreliable. Chaos is the name for behavior in which tiny differences in starting conditions can grow rapidly in time. It is known from classical systems such as weather, fluid motion, and some orbital arrangements. Chaos does not mean absence of law. It means that lawful systems can become difficult to predict in detail because the required precision of the starting state becomes unreachable. Quantum computing does not remove this general fact. It may offer new tools for certain calculations, but it does not grant exact knowledge of every starting condition in a complex natural system. The limit comes from the relation between rules, data, and sensitivity. The second limit is computational complexity. Complexity, in this setting, concerns how the resources needed to solve a problem grow as the problem becomes larger. Resources include time, memory, operations, and device quality. Some problems grow gently, so larger cases remain manageable. Others grow so quickly that direct solution becomes impractical. Quantum computers change the resource landscape for selected tasks. They may reduce the growth for some problems, and they may model some quantum systems more naturally. However, they do not make all hard problems easy. Complexity theory, the study of these growth patterns, gives no support to the idea that quantum machines erase every computational boundary. The third limit is measurement. A quantum state may contain rich structure, but a measurement returns a finite classical outcome. To learn a probability distribution, the device must run many times. To estimate a value, it must gather enough samples to reduce uncertainty. Sampling is the process of collecting individual results from repeated trials. In some cases, a quantum algorithm can reduce the number of samples or operations needed. In other cases, the cost remains large. The state inside the machine is not a library that can be opened page by page. It is a physical arrangement that offers evidence only through allowed measurements. The fourth limit is verification. A prediction has scientific value only when there is a way to test, compare, or bound its reliability. For small systems, classical computation or direct experiment can check a quantum result. For large systems, checking becomes more difficult. A machine may produce an answer for a problem chosen because classical checking is hard. This creates a careful tension. The result is interesting because it reaches beyond ordinary methods. Yet trust must still be built through benchmarks, simplified cases, internal consistency, and independent approaches. Quantum computers also reveal a limit in language. Ordinary words such as state, outcome, path, and possibility carry meanings from daily experience. In quantum theory, these words are disciplined by mathematics and experiment. A state does not always mean a hidden catalogue of definite properties. An outcome is not always one item chosen from a pre-written list in the classical sense. A path in an algorithm may be a contribution to an amplitude, not a route travelled by a small object. When language becomes too loose, prediction appears more mysterious than it needs to be. When language is kept precise, the mystery becomes a boundary of intuition rather than a failure of science. This boundary affects claims about the future of the field. It is reasonable to expect progress in hardware, algorithms, and applications. It is not scientifically careful to state that quantum computers will soon predict everything from weather to markets to human behavior. Many such systems are open, noisy, adaptive, and sensitive to information that cannot be fully captured. Human social systems also include choices, institutions, feedback, and incomplete data. The limit is not only the machine, it is the world being modelled. The deeper lesson is that prediction in science is always an agreement between a question, a model, data, and a method. A good prediction is not a claim to absolute control. It is a reliable answer within a defined range. Quantum computers may widen that range for important problems, especially where quantum structure itself blocks classical calculation. They may show how matter behaves, how energies arrange, how probabilities shift, and how certain patterns emerge. They also show that some information remains accessible only statistically. Some problems remain resource-heavy, and some systems resist long-term precision. In this region, the truth is not that reality is beyond knowledge. It is that knowledge has shape. It comes with conditions, error bars, sampling limits, model choices, and physical costs. Quantum computing makes this shape visible because it works so close to the rules that govern small systems. It strengthens prediction in chosen places while preserving humility elsewhere. The machine calculates, samples, compares, and estimates. It extends the reach of science. But it does not abolish the horizon where uncertainty, complexity, and incomplete information remain. Reality as information is a careful scientific idea, not a claim that the world is only a message on a screen. In quantum computing, information is always physical. It is held by circuits, atoms, ions, photons, spins, fields, and measuring devices. It is changed by operations that require energy, time, control, and contact with instruments. The word information does not float above matter. It describes the way physical systems can be prepared, related, transformed, and recorded. At this inner layer, the machine shows that the boundary between physics and information is not a matter of convenience. It is part of how the small world is described and tested. In ordinary life, information often seems separate from the object that carries it. A sentence can be printed on paper, stored on a hard drive, spoken through air, or displayed on glass. The meaning may survive across many carriers. This makes information feel almost weightless. Physics gives it a body again. Every record must be carried by some physical state, a mark of ink, a magnetic grain, an electrical charge. Or a pulse of light must differ from another possible state in a way that can be preserved and read. In classical computing, this physical fact is often hidden by stability. In quantum computing, it becomes impossible to ignore. Quantum information is not simply ordinary information made small, it obeys different limits. An unknown quantum state cannot be copied perfectly. A measurement does not generally reveal the whole state. Entanglement can store information in relations rather than in separate parts. Phase can affect future outcomes while remaining invisible to a single direct reading. These features are not decorations added to information. They define what information can mean inside quantum theory. A qubit is therefore not only a smaller bit, it is a carrier of a different kind of physical possibility. This does not prove that reality is unreal. The opposite lesson is more grounded. Quantum information works only because the physical world is consistent enough to prepare, control, and measure. If atoms, circuits, and photons did not follow stable rules, quantum computing could not exist. The strangeness of the theory is not a sign that the world is imaginary. It is a sign that everyday categories are not deep enough to describe all physical behavior. Reality remains present as the laboratory bench, the cold apparatus, the material chip, the detector signal, and the repeated record. Information is one language through which that reality becomes predictable. The link between information and physics appears in the cost of erasing and storing records. A computer memory does not change without physical consequences. When a record is reset, heat may be released into the environment. This connects information to thermodynamics, the study of heat, energy, and work. The point is not that every act of thought heats the universe in a dramatic way. It is that information processing belongs to physical law. A record is not an abstract ghost. It is a state of matter or energy, and changing it means changing the world in some small measurable way. Quantum computing deepens this connection because the information being processed cannot be separated from the rules of quantum mechanics. The state of a register is not a hidden classical list stored in a strange box. It is a quantum state with amplitudes, phases, and possible entanglement. The operations are not ordinary switches acting on secret definite values. They are controlled transformations of the state. The final measurement is not a complete download of the inner description. It is a physical event that creates a classical record. At every step, information and physical process remain joined. This joining changes how reality is described. In classical thinking, an object seems to have properties first, and information about those properties comes later. A stone has a position, a mass, and a shape, whether or not a person writes them down. In quantum theory, some properties do not fit the same simple pattern before measurement. The theory predicts probabilities for possible outcomes of chosen measurements, and those predictions depend on the prepared state. The information is not merely a human list of facts about a completely classical object. It is part of the structure used to connect preparation with outcome. This does not mean that human knowledge creates the physical world. A detector can record a result without a person watching at that moment. Stars shine, atoms decay, minerals form, and photons travel without waiting for human attention. The role of information in quantum theory is not a license for vague claims about consciousness. It is a disciplined way to describe what can be known, how it can be known, and what physical arrangements make a record possible. Quantum computers follow this discipline. They do not think reality into being. They process states according to lawful transformations and then produce records that can be compared. The word reality therefore becomes quieter. It no longer means only the solid world of large objects with fixed appearances. It also includes the underlying rules that allow probability, phase, relation, and measurement to fit together. These rules are not visible like a rock or a wave on water, but their effects are measured with great accuracy. A quantum computer is one of the clearest instruments for showing this because it must preserve the difference between a coherent state and an ordinary mixture. It must use phase before phase is lost. It must use entanglement before the environment takes the relation away. It must turn the final result into a stable record. At this layer, the so-called truth about reality is not terrifying in the scientific sense. It is demanding. Reality allows information to exist in forms that cannot be treated as simple hidden facts. It allows relations to matter as much as individual parts. It allows probability to be structured by phase. It allows measurement to produce definite records without giving direct access to the whole prior state. These facts do not dissolve the world. They refine it. Quantum computing makes this refinement visible by forcing information to remain physical from beginning to end. The machine stores no free-floating meaning. It holds carefully prepared states in vulnerable carriers. It changes them through controlled operations. It reads them through measuring devices that return ordinary records. The lesson rests in that chain. Information is not separate from reality, and reality is not reduced to information alone. They meet where physical systems carry possibilities, where operations shape them, and where records become part of the world that can be kept. The interpretation boundary is the place where the tested rules of quantum mechanics meet the human desire for a picture. A quantum computer can be built, controlled, calibrated, and measured without settling every question about what the quantum state means. The equations guide the device with great accuracy. The records appear with the predicted probabilities. The hardware either follows the model well enough or it does not. Yet beneath this practical success, physicists and philosophers still examine how the same experimental fact should be understood. This region is not a failure of science. It is a boundary between prediction and explanation, between what the formal rules do and what kind of world those rules describe. An interpretation of quantum mechanics is a way of explaining the meaning of the theory while preserving its tested predictions. The main interpretations do not usually disagree about the ordinary results of standard experiments. They disagree about what is happening behind or beneath those results. They ask how a quantum state relates to physical reality, what measurement changes, whether probabilities are basic, and whether the definite outcome recorded by an instrument is the whole story or only one part of a larger description. The answers differ, but the laboratory facts remain the anchor. The Copenhagen tradition is one of the oldest ways of speaking about quantum theory. It does not form a single perfectly fixed doctrine, but it generally places strong emphasis on the role of measurement and on the limits of describing quantum systems with ordinary classical images. In this view, the quantum state is used to calculate the probabilities of measurement outcomes. The measuring arrangement matters because it defines what can be asked of the system. The theory does not always claim that a particle has every classical property before a measurement reveals it. It instead treats the experimental context as central to what can be meaningfully said. This view fits much laboratory practice because it keeps attention on preparation, measurement, and prediction. It avoids unnecessary pictures when those pictures go beyond what experiments require, yet it can feel incomplete to those who want to continue a story of what exists between preparation and record. The formal rules say how to calculate. The interpretation advises restraint in speaking beyond those rules. Its strength is caution. Its difficulty is that the boundary between quantum system and classical measuring device can seem more like a practical division than a fully explained physical process. Collapse interpretations take the definite outcome as a real physical event. In such views, the quantum state changes from a spread of possibilities into one result through a process that is not merely an update of knowledge. Some versions add new physical mechanisms that cause collapse under certain conditions, such as when systems become large or complex enough. These ideas try to explain why everyday objects do not appear in visible superpositions. They also seek to make measurement a physical process rather than a special rule. Their challenge is that added mechanisms must remain consistent with the many precise experiments already supporting standard quantum theory. The many worlds interpretation gives a different picture. It keeps the smooth evolution of the quantum state and treats measurement as an ordinary quantum interaction. In this view, when a measurement occurs, the combined state of system, instrument, and environment develops separate branches corresponding to different outcomes. Each branch contains a definite record from within that branch. There is no special collapse added to the theory. The attraction of this view is that it uses the same quantum rule everywhere. Its difficulty is the weight of its meaning. It implies a vast branching structure, and it must explain how ordinary probabilities arise for observers inside those branches. Pilot wave theory offers another path. It treats particles as having definite positions guided by a wave-like quantum structure. The guiding structure evolves according to quantum rules, while particles follow paths determined by it. This gives a clear picture of definite outcomes without ordinary collapse. It also shows that quantum predictions can be recovered with a deeper underlying description. However, the theory is explicitly non-local, meaning the guiding relations do not fit the simple classical idea that distant systems carry entirely independent local instructions. This non-local character aligns with the lessons of entanglement experiments, but it sits uneasily beside the clean spacetime intuitions of relativity. Relational interpretations place emphasis on relations between systems rather than on absolute properties held independently by objects. In such views, the state or facts associated with a system can depend on the physical interaction through which another system gains information about it. This does not mean that reality is invented by opinion. It means that quantum theory may describe facts as arising in interactions rather than existing as a single complete catalogue visible from nowhere. This kind of interpretation fits naturally with the idea that entanglement and measurement are relations among physical systems. Information-based interpretations take the quantum state as a tool for organizing expectations, knowledge, or commitments about future records. These views often stress that the theory is a rulebook for agents using information about preparations and measurements. They can clarify why measurement changes the state assigned to a system, since new information changes expectations. Their challenge is to explain what physical world supports these experiences and why the rulebook has exactly the structure it has. A purely informational language must still connect to the stubborn reality of detectors, atoms, chips, and laboratory records. Quantum computers do not choose among these interpretations by their existence alone. A superconducting processor, an ion trap, or an atom array follows the operational rules that all major interpretations are built to respect. The gates work or fail according to measurable fidelities. The output distributions agree or disagree with calculated predictions. The interpretive question remains deeper than the engineering question. It concerns the meaning of the successful rules, not their basic usefulness. In this region, the unsettling truth is modest. The same observed world can be described by several serious interpretations that preserve the known facts while giving different accounts of what lies beneath them. Reality is not made less real by this. It is made less easy to force into one familiar image. Quantum computing sharpens the issue because it turns the debated features of the theory into working resources. Superposition, entanglement, and measurement are not only puzzles discussed at distance, they're operations, errors, records, and probabilities inside machines. The boundary remains calm and exact. The facts are stable. The meaning is still carefully argued. At the deepest mathematical layer, quantum computing becomes a study of states, transformations, and probabilities. The visible machine has already fallen away into a quieter form. Cables, chips, atoms, lasers, and detectors remain necessary in the laboratory, but the inner description is written in a language that treats physical systems through abstract spaces and rules. It allows physicists to calculate what a device should do before any record appears. The mathematics does not replace the physical world. It gives a precise way to describe the patterns that the physical world repeatedly shows. The central object is the quantum state. In the formal theory, a state belongs to a Hilbert space. which is an abstract mathematical space used to hold the possible states of a quantum system and to define how they combine. It gives a disciplined arena where superposition can be represented, where phases can be compared, and where measurement probabilities can be calculated. A classical bit needs only 2 allowed values for its simplest description. A qubit needs a richer description because its possible states include controlled combinations of the 2 reference outcomes. The state is not a visible object inside the device. It is a formal description connected to preparation and measurement. If the system is prepared in the same way many times, the state allows calculation of how often different outcomes should appear under a chosen measurement. This is how the abstract core remains tied to evidence. The mathematics earns its meaning by predicting patterns in records. With experiment, it becomes the working grammar of quantum physics. Probabilities enter through a rule that connects the state with measurement outcomes. The state contains amplitudes, and the squared size of an amplitude gives the probability for a related outcome when the proper measurement is made. The amplitude itself is not a probability. It carries phase as well as size, because amplitudes can combine before probabilities are produced. Quantum theory allows interference. This is the formal reason a quantum algorithm can be designed to make some outcomes grow more likely and others fade. Transformations are the next part of the core. In ideal quantum mechanics, the state changes through operations that preserve the total probability and keep the structure of the space intact. These transformations are reversible in the ideal description. Reversible means that, in principle, the operation can be undone if the system remains isolated and no measurement has fixed a record. This reversibility is one reason quantum gates differ from many ordinary logical operations. A classical operation can erase information, such as turning 2 different inputs into the same output. An ideal quantum operation cannot casually do that inside the coherent part of the computation. It must move the state in a way that remains mathematically balanced. A quantum gate is therefore a transformation in this abstract space. A single qubit gate changes the state of one qubit, often by changing the relation between basis states and phases. A 2-qubit gate can create or modify entanglement, making the joint state of the pair unable to be written as 2 separate single-qubit states. Larger circuits are built by arranging many gates in sequence. The circuit is a formal recipe for how the state should move through the mathematical space before measurement turns part of that motion into a record. Tensor products form the mathematical way separate systems are combined. A tensor product is a rule for building the state space of a joint system from the spaces of its parts. For ordinary independent objects, combining descriptions may feel like placing lists side by side. For quantum systems, the combined space contains states that are not separable into such simple lists. This is the home of entanglement. The formal growth of the joint space explains why quantum systems become difficult to simulate classically. It also explains why a quantum computer must be controlled carefully. The state of many qubits can occupy a structure too large to describe by tracking each qubit alone. Measurement appears in the core as a rule for extracting probabilities and updating the description after an outcome. A measurement does not reveal the whole state. It selects from the possibilities defined by the measurement arrangement. The formal rule gives the probability of each outcome and the state associated with that outcome afterward. This rule is practical enough to guide experiments and strange enough to motivate interpretation. In the mathematical core, it connects abstract state to stable record. Density matrices extend the description when knowledge is incomplete, or when a system is entangled with an environment. A density matrix is a mathematical object used to describe both pure states and statistical mixtures. A pure state is the most complete state description allowed by the theory for a system. A mixture represents uncertainty or loss of accessible quantum order. This language is essential because noise, imperfect preparation, and environmental contact cannot be ignored. It allows the same formal core to describe coherent evolution and the gradual fading of coherence. The mathematics also contains limits. The no-cloning theorem follows from the structure of quantum states and transformations. It states that an arbitrary unknown quantum state cannot be copied perfectly. This is not a manufacturing limit or a weakness of present instruments. It is a consequence of the formal rules themselves. Uncertainty relations also arise from the structure. They express that certain pairs of measurable quantities cannot both have perfectly sharp values in the same state. These limits are built into the relation between state, transformation, and measurement. At this depth, the word reality becomes tied to invariance. An invariant is something that remains unchanged under an allowed change of description. Different laboratories may choose different bases, diagrams, or hardware platforms, but the calculated probabilities must agree with the same physical records. The formalism provides a way to move between descriptions without changing the measurable content. It does not insist that the quantum world resemble a small mechanical model. It insists that preparations, transformations, and measurements fit together consistently. The deep mathematical core is quiet because it does not need dramatic images. It holds the rules that allow a quantum computer to be designed, tested, and understood. States live in abstract spaces. Gates transform them. Tensor products join systems. Amplitudes interfere. Measurements produce probabilities and records. Noise is described by broader state tools. Limits arise from the same structure that gives power. Nothing in this core says that reality is unreal. It says that reality, at this scale, is best described by a formal language in which possibility has shape, relation has structure, and knowledge becomes precise only through physical measurement. At the quiet inner center of quantum computing, the dramatic language falls away. The machine does not reveal terror as a scientific property of the world. It reveals a deeper precision beneath familiar appearances. The table, the lamp, the hand of an instrument, the metal wall of a laboratory, and the cold chip inside a refrigerator all belong to one physical reality, at large scales. That reality appears stable and definite because countless interactions with the environment constantly produce durable records. At smaller controlled scales, the same reality allows states that are not captured by ordinary images of fixed parts carrying fixed properties. The contrast is not a break in nature. It is a change in the level of description. This center is not reached by leaving matter behind. It is reached by following matter inward until its ordinary face becomes insufficient. The qubit is never detached from the world. It is a circuit, an atom, an ion, a photon, or a spin placed under conditions that allow quantum rules to become useful. The rules do not wait for the machine. They are already present in matter, in chemical bonds, in light, in solids, and in the behavior of atoms. The machine makes them visible as computation because it holds them in a form that can be prepared, changed, and measured. The unsettling part is not that reality becomes chaotic or unreal. The unsettling part is that reality remains orderly while refusing to obey some of the simplest habits of human thought. Ordinary thought expects every object to carry a complete set of properties before any test. It expects information to be copied if it is known. It expects a whole to be explainable by separately describing its parts. It expects uncertainty to mean only a lack of knowledge. Quantum theory shows, through repeated experiment, that these expectations are not always reliable at small scales. The world is not less lawful than expected. It is lawful in a different way. A quantum computer gives this lesson a practical body. It uses superposition not as a vague mystery, but as a prepared state with phase and probability. It uses entanglement not as distant magic, but as a shared state that produces tested correlations. It uses measurement not as a human act of wishing, but as a physical process that creates a stable record. It uses error correction not as denial of fragility, but as a method for protecting order against noise. Each part of the machine is a reminder that the strange features of quantum theory are not decorations in a textbook. They are working features of physical systems. The word revealed must therefore be held carefully. A quantum computer does not reveal reality by making a single statement that replaces all previous science. It reveals by functioning. It reveals by showing that a controlled quantum state can be used as information. It reveals by making interference useful, by making entanglement operational, and by making the limits of measurement impossible to ignore. Its truth is not hidden in a single output. It lies in the entire discipline chain from preparation to record. When the chain works, the world confirms that these quiet rules are not optional stories, they are part of what matter does. This is why the word terrifying belongs more to wonder than to fact. Fear often appears when familiar categories lose authority. A classical picture feels comfortable because it resembles daily life. A quantum picture feels strange because it asks for another kind of clarity. It does not show that the world is deceptive. It shows that the world is deeper than the senses alone suggest. The solid surface of experience is not false. It is the result of many small processes combining into stable, large-scale behavior. Beneath that surface, reality has structure that cannot be flattened into common sense without losing accuracy. The deepest meaning is also modest. Quantum computers do not answer every question about existence. They do not settle every interpretation of quantum mechanics. They do not make all predictions easy or all knowledge complete. They remain physical devices with errors, limits, costs, and uncertain timelines. Their importance comes from the fact that even limited machines already force a careful respect for the quantum structure of nature. They show that information, matter, and measurement are woven together. They show that relations can be as important as individual parts. They show that probability is not always a sign of ignorance alone, but can be shaped by phase and constrained by physical law. In the calmest view, reality is neither the simple world of everyday instinct nor an unknowable darkness beyond science. It is a layered physical order. At one level, stones rest, water flows, planets orbit, and instruments record. At another level, states combine, amplitudes interfere, and entangled systems resist separation into independent stories. Both levels are real. The familiar level is not an illusion, and the quantum level is not a fantasy. They are connected by scale, interaction, and the growth of stable records from fragile states. The inner center therefore holds no final drama. It holds discipline. It asks that language become slower and more exact. It asks that claims stay close to preparation, operation, measurement, and evidence. It asks that uncertainty be named without being exaggerated. It asks that the limits of intuition not be mistaken for the limits of reality. Quantum computers stand at this center as instruments of humility. They show that the world can be knowable without being easily pictured, predictable without being fully exposed, and precise without being simple. The truth they reveal is not that reality is terrifying. It is that reality is patient, structured, and less human shape than ordinary thought assumes. It permits stable records and delicate possibilities, visible facts and hidden phases, separate objects and deep relations. A quantum computer is a small controlled opening into that order. It does not tear the surface away. It lets the surface become understood as part of a wider whole. At the center, the lesson rests quietly. Reality remains real, but it is not required to resemble the first picture the mind makes of it. The machine settles back into silence as the thought of it widens and becomes simple again. A quantum computer remains a human instrument, made from matter, guided by mathematics, and limited by noise. It does not stand outside nature. It belongs to nature completely. Its cold circuits, trapped atoms, passing photons, and measured records all rest inside the same physical order that shapes stars, stones, oceans, and the quiet air of a room. The strange rules do not arrive from elsewhere. They have always been present, working beneath the calm surface of ordinary things. At the end of the path, the question of reality becomes softer. The world does not need to be less real because it is less familiar. It does not need to be frightening because it is deeper than daily instinct. Large objects keep their steady forms because countless interactions make records stable. Small systems, protected for a brief time, show another kind of order, one that carries phase, relation, probability, and measurement. Both belong to the same universe. Quantum computing gives no final answer to every mystery. It gives a clearer respect for the limits and strengths of knowledge. It shows that prediction has boundaries, that information has a body, that measurement is a physical act, and that certainty is not always the first layer of truth. It also shows that careful work can turn delicate behavior into something useful. The result is not a collapse of meaning, but a refinement of it. Reality remains patient. It allows familiar surfaces and hidden structures. It allows stable facts and fragile possibilities. It allows machines to ask narrow questions and receive narrow answers. In that quiet balance, the deeper world does not shout. It simply continues, precise and calm, holding more than common sense can picture, and still holding everything that common sense calls real.